for showing up, and yeah, I'm full of admiration for you guys that can stay here 4 weeks, listen to so many lectures. Okay, so one usage, so I spent 4 lectures doing the linear theory of 2 layers neural networks, and we learned, I think, some things. And what are the uses of this? So in this lecture, I would like to discuss it a little bit and connections to other results. And one usage of this is to derive very easily separation results between kernels either NT kernels or other, and neural nets. So let me give you the simplest of such example. It's really elementary, but I'll go through it in detail because I think it's instructive and it's a nice exercise. So I'll take my setting, that is data that are uniform in the sphere in d dimension, and the yi that are f star xi plus epsilon I, and I'll take a special function form of this function f star that is a single neuron. Okay, so there is some vector that I'll call u star, and my function is simply applying one neuron to x. Okay, this is, in statistics, people call it sometimes a ridge function. Okay, because it depends only on one direction. Right, so now what we have to do, we know exactly what is the risk of this for any inner product kernel. And so we know that the prediction error at f star for any inner product kernel is basically, if the sample size is less than d to the L plus 1, say minus epsilon, the risk is the projection of the function onto polynomial bigger than L, of degree bigger than L2 square plus molo of 1. Okay, and so all that we have to compute is this object, and we know the same is true. Same risk for 2-layer neural networks if ND is much bigger than N, okay, in the overparameterized regime. Okay, so all of that you have to do is to compute this. So let's do the exercise of computing this projection. So we have to decompose this f star in spherical harmonics. So it's convenient to look at a basis of spherical harmonics in which we have invariance under u star. So I claim that for any L, there exists a unique QL of x, QL in BL, that is the span of the spherical harmonics, let's say for any M, just not to confuse, of spherical harmonics Mj, that is invariant under rotations, okay, such that Qm of x is equal Qm of Rx for any, or let's call this M or Sx, for any S rotation that keeps U star invariant. Okay, this is easy to check. It's just you take any spherical harmonics and then you average over rotation, and then there must be only one. Okay, and so what happens is that the spherical harmonic, of course, has a form QL of x must have the form, since it's invariant are the notation of a polynomial of degree m times evaluated on the inner product u times x. Okay, because any function that is invariant on the rotation on the sphere must depend only on this one-dimensional projection and must be a polynomial of degree m. Okay, and what this polynomial satisfies, so here I assume for simplicity u star of norm 1. What condition does this polynomial satisfy? Well, it must satisfy the orthogonality condition. So qm prime is delta mm prime. So there exists unique normalized polynomial. And so what does this mean? It means that if I write it in terms of this, that the integral of p, when you do the integral, substitute this over this one, and I can reduce this to a one-dimensional integral. Where what is tau d? Tau d is the probability distribution or probability measure of u star times x when x is uniform in the sphere of radius square root of d in d dimension. Right? I have to do this integral. This is an integral over, so what is this product? This product is qm x qm prime of x mu 0 dx, or mu dx, where mu is the uniform measure over the sphere. When I substitute this, I can reduce it to a uniform, a one-dimensional integral with respect to the measure of one-dimensional projection. Okay, does that make sense to everybody? Okay, so one thing that we know, one beautiful fact about high-dimensional geometry is that if you look at the one-dimensional projection of the sphere, they are Gaussian. So low-dimensional shadows of high-dimensional spheres are Gaussian. And so these are approximately Gaussian. So more concretely, tau d converges to the standard Gaussian measure. So let me be a little bit quick here, and I claim that this implies that PMD, let's say that PM converges to some limit as diff to infinity. This implies that PMD, PM infinity, are orthonormal polynomials with respect to the Gaussian measure.
What kind of scaling are you using? Because I was expecting the variance of the Gaussian to depend on the dimension, right?
Right, but here I'm taking, this is the reason why I'm taking the radius of the sphere's
Just by taking the
square root of d, right? So this means that x squared is equal to d. So this means that each entry has variance 1. Any other question? Okay, now we know what are the orthonormal polynomials with respect to the Gaussian measure. Hermite polynomial. So PM infinity is the mth Hermite polynomial. Very nice. And so what does this mean? It means that this coefficient here, if I expand f star into the basis of spherical harmonics, this must look like sum over L equals 0 infinity of some coefficient sigma LD, let's call it sigma at LD, PLD x u star. And as d goes to infinity, this coefficient converges to sigma L infinity, which is the projection of sigma onto Hermite polynomial. So it's the expectation of sigma of G okay. This is a nice exercise that we did. And so what does this imply? It implies that this projection onto polynomial onto spherical harmonics of degree L of larger of S star in L2 of the sphere must be about, or must converge as d goes to infinity, to the sum of this coefficient m equal L plus 1 to infinity of sigma of these things, right? So let me write it like this: of sigma times HEM with respect to the Gaussian measure square. So this was a nice exercise, but in reality we need only one factor. I need only one consequence of this. So this means that all of these projections are non-zero. Does that make sense to everybody? Any question? So this function, this very simple function, to expand it in spherical harmonics as non-zero coefficients of any order. So what I need is this strictly zero, strictly positive. Well, yeah. So this is an assumption on sigma, right? But if you take basically pretty much any, for instance, if you take ReLU or if you take tangent, unless sigma is a degree L polynomial, that will happen, right? So unless sigma is a degree L polynomial. So we have the following corollary that we proved. Corollary. Assume sigma not a polynomial, and n for any L integer, if n is less than d to the L plus 1 minus epsilon, then, or L plus 1, that doesn't matter, limit, or let's say the risk at f star lambda of nt or krr, etc., is bigger than a constant bigger than 0 plus more log 1. So you need a non-polynomial number of sample in the kernel method. In the NTK method, you need a super polynomial number of sample to learn the simple ridge function. So this was an example that appeared in a paper of ours with Theodore and Song, and appeared in a paper. They have kind of not exactly this form of the statement, but similar form by Yehudai and Ohad Shamir a few years ago. Okay, so the form of their statement is different. They show that for the risk to be to zero, go to zero, then the sample size has to grow super polynomial in the dimension. Here we have a lower bound for any polynomial. So this is a bit disappointing, right? Okay, to somebody like Nati is not surprising, but it's a little bit disappointment. So here, of course, I'm assuming that kernel is always inner product kernel. Yeah.
No, the expression is because there is other things for any kernel, not just.
Sorry?
There is all the Udashimir result is for any kernel, not just for inner product.
This result,
Yes.
this one,
No, the Udashimir result.
the Udashimir,
for any kernel.
is it for
Yes.
for any kernel? Okay, depends where. I don't think it's.
Other quantifiers is a bit different, but it's for any kernel.
But okay, it's for any kernel, but it must be in minimax sense, right?
Yes.
Because
Yes,
yeah,
of course, if you have
Yeah.
a fixed,
yeah. If you use a kernel that knows where U star is, then the problem is trivial, right? You can. So on the other hand, these functions are very simple to learn, right? So this function f star equal fx equal sigma of u star times x depends only on d parameters. Okay, so it should be easy to learn. So should be possible to learn. With the right inductive bias from order D samples. So here is one example of how to do it. Here is one example. You can do it with a one neural network. That is, if you minimize r hat of theta, which is the expectation, okay, the population expectation, the sample expectations. Okay, suppose that you have data that are like this. If you can try to fit a single neuron, right? And if you fit a single neuron, this means minimizing this cost, right? This is a single neuron cost. And okay, now this boils down to analyzing this empirical risk minimization problem. And so let's call theta hat equal argmin of theta and here is a proposition. This is really a consequence of a more general theorem that we have in a paper with U by. It says the following: if sigma prime is bounded away from 0 and sigma third, I think sigma third is bounded, then, okay, let's say C minus 1, then GD on R hat and theta converges to theta hat n globally. Then with high probability, globally. And theta hat n satisfies some bound like this. In particular, so what is this saying, right? So there is this p-dimensional parameters, and this is saying that there is a special vector u star, and this theorem says that gradient descent has a unique fixed point that is u star, and whenever you start, you know, the gradient flow brings you there. Okay, and for that to happen, is sufficient that, you know, the sample size basically is much bigger than the dimension modulo log factors, right? So in particular, so the risk will depend continuously. So if theta hat n is close to u star, then the test error will be close to u star. You will have, if n is much bigger than d log d, then the population, the test error of this model goes to 0. So this is, you know, in my view, is probably the simplest example of, you know, a reasonable separation between kernel and neural networks. Yeah.
A question: how sensitive is this to the fact that in the risk there you use the same sigma as in the star?
Yeah, good question. Okay, you know, I don't think it's very sensitive, but the theorem we proved it for the. So okay, open.
Well, for the kernels, I could say, oh, it all boiled down to the fact that f star was not a polynomial.
No, for the kernel, it doesn't matter that this sigma is the same.
Exactly, but I could think about it. Oh, if sigma was a polynomial of degree d, then degree L, then I would be okay. And here I could think, oh, maybe it's similar. The sigma kind of could be able nicely represent that other sigma.
Yeah, if sigma is a polynomial of degree L, here, I mean, so here we are minimizing, we have two sigmas, right?
Say that there we have, I don't know, sinus and here rim.
Right, so what happens, open. Oh, I want to use red for open. As far as I know, this form of the theorem is not known there. Generalize for yi equal some phi of u star transpose xi plus noise. And I can give for you, you know, some special function phi for which this theorem doesn't generalize. For instance, if you take phi to be a high degree Hermite polynomial, then it will not generalize. You will need more sample because you get stuck at the equator. But if you take phi that satisfies this kind of conditions, so phi is monotonically increasing with the first derivative bounded away from 0, basically what matters is what is the gradient of the risk of the population error at initialization. Okay? So we have a general theorem in this paper that says, okay, if the population error basically behaves well, then the empirical error also behaves well, and so all the matter is studying her. And okay, nobody has done it for a general phi, but that I think it's or perhaps somebody has done it.
I think there's work for a general monotone phi, looking at isotonic regression, and basically for any monotone phi. Okay, that would exactly with gradient descent.
Right. Yeah, I mean, if phi is monotone, and you ask me just the question, can I learn it? Here is a very simple trick. So let's open the parentheses, because this is a nice trick to keep in mind. if I'm not constrained to do gradient descent, if I'm not constrained, and to GD, then I can do the following. I can just compute a first estimate that is 1 over n sum over I yi xi. Okay, and this for n larger than d, this will concentrate around, for n much larger than d, this will concentrate around the expectation of y times x. And what is this? This is expectation of phi of u star x times x. And you see that if x is isotropic, then this is proportional to u star. This is a constant times u star. Okay? So if you allow me to do this very simple operation, that essentially is equivalent to take the gradient at the initialization, then I can get a very good guess of u star at step 1, right? And now I normalize it, and now I localize the problem. After the first step, basically in the first step I can get very close to u star. Okay, so in the first step I get around here. At that point I can either declare victory, or if I'm more careful or demanding, I can run a small gradient descent here, right? So for a general u star, if you don't ask the question about, but okay, here I stated a theorem because I'm assuming that I'm married to gradient descent, and so I want to live with gradient descent for.
This is true if n is larger.
Yeah. So.
Oh, yeah, sorry.
Yeah.
I see.
And much bigger. So you probably let's throw in a log factor since we are in between friends. Okay.
Andrea, to be married to gradient descent on your loss, right?
Yeah.
Gradient descent is different about even, right? So you have to be.
Yeah. That is. That's. Yeah. I'm very married to it. Okay. So now. Okay. So there are countless other separation examples, more interesting. There was a poster about this by Stephanie than this one, but I think this is the simplest one. And what is nice about this, it conveys an interesting intuition that is, kernel or isotropic kernels that come from neural network are not good at learning functions that depend strongly on a low-dimensional projection of the data. Right? So if what matters, for instance, if your image is a small subset of the pixel or a small subset of the frequencies, for instance, low frequencies are important, neural networks are bad at that. And okay, we have simulations of that type that you can look up in the papers. Okay. But okay, let's stick to this example. And now I want to summarize what we know, right? And discuss it a little bit with you. So what do we know? So let's stick to this specific example. Star of x. With the caveat that this can be, modified to a general sigma. In fact, I could add a finite combination of these and probably things will not change. But let's stick to this example. And now what is the risk after I run a gradient descent as a function of the width of the network, right? Since we talked so much about width, okay, and say that my network is 1 over square root of n, sum over I 1 to n, ai sigma of wi transpose times x, and for simplicity all the ai are plus minus 1, not trained. So here we have a point, so we have n equal 1, 2, 3, etc. So we have a point here that is the theorem here. it says that the risk, let's say also that the sample size is subpolynomial, so it's less than d to the much bigger than d and much smaller than d to some constant power. Okay, so here I will get 0. That is that theorem, or I'll get something that goes to 0. And then what else do we know? We know that for very large n, this was the corollary that I gave before. This converges to some limit that is bounded away from 0. Let's say that this is dl plus 1. So this will converge to this projection bigger than L of f star 2 that is bounded away from 0. Okay, so we know that the risk, so what we know that the risk of the associated kernel so this is, okay, or the NTK will be very close to that. That this is the corollary before, and this will be very close to that, what we proved in last lecture, as soon as we move above width that is what? Sample size over dimension. Modulo log factors. Okay, so this is there, up there. And what we know about the real neural network, well, what we know rigorously is that you have to go, as I said, the best condition for the NTK to be correct that has been proved rigorously is nd bigger than a constant times n square. So this puts us here. Okay? So this is neural nets. Or perhaps I should use right. Well, we proved in the first lecture, I didn't prove, but I stated a theorem and I proved part of it, that if nd is bigger than n squared, the risk of neural networks trained by gradient descent for a random initialization is very similar to the risk of the NTK.
In that regime?
Sorry? Yeah, under this regime, this nd bigger than n squared. This is the condition. You take this neural network. Well, there is the condition that has to be initialized symmetrically. But you take a neural network, well, perhaps not even that in this case. So you take a neural network, you make it big enough so that this is true. And the risk, the prediction error is very close to the NTK prediction error, up to small o of 1 thing. This is this paper of, is in Oimak, Sotano Kotabi, and you can read the precise form that with the prediction error also in this review paper with Bartlett and Rackley. All of this is under this very simple data model, right? So they prove, and we put some epsilon and delta additional that these two are very close. And what I did in lecture, 3 and 4 is that the green line, they proved that the red and the green are very close. And what we proved in lecture 3 and 4 is that the green is very close to this. And what I proved right now is that this is bounded away from 0. Okay? Does that make sense? So we proved for nd much bigger than n squared, we know that the risk of neural networks is very similar to the risk of NTK. And we proved also that this is very similar to the risk of polynomial regression with respect to the degree L, and we know that this is equal p bigger than L. So we are in this interesting situation. Now, I don't know what happens when I fit 2 neurons, 3 neurons, etc., but this can be can be surely done at least to the level of physics by writing ODs from the evolution of the neurons and solving ODs in 4 parameters or 4 dimensions and solving them numerically. And my guess is that here you get also 0 and 0. So what you get is somehow this interesting situation where here we don't know what happens, but the risk of neural network and the gradient descent, at a certain point, can be non-monotone, but at a certain point deteriorates when you take the widths larger and larger.
So one could ask the question of whether this is due to width itself or whether it's due to the neural tensor kernel parameterization. In the mean field parameterization, what happens at...
Okay, exactly. So is this a problem of width? This is an excellent question because this was the question that I was about to ask, right? Right? Yeah. Is this due to width? Is it true? By the way, is this true that wide neural network are bad? By the way, there is a paper that appeared, I think a few weeks ago by Pritum Nakiran, where they do this kind of things, take the anti-scaling and do it for some more realistic data set than this, and then they show that indeed the behavior is like this. If you take the NT, actually, if I remember correctly, I saw some plot where it does like this, which makes sense. If you take a function that is more complex than this, then if you take the target function that is 2 neuron, you will see something like this, right? First you have to increase the width, and then we'll go down up. Right? Because 1 neuron here will be limited by approximation, and here will converge to the NT. Okay, so this is Pritum Nakiran. In fact, he gave this talk, and I was in the audience, and he asked, do you expect this or this? And I said, I expect this. But yeah, it's a very nice experiment that they did.
Because of the square root of n.
Right. So this is where I want to get. Right. Okay. So is this? I claim that it is because the 1 over square root of n scaling is wrong. I mean, I've been saying this for a while, but. Okay, so here is another. So here is a slightly cheating way of doing it. So my answer is no. The problem is that we should scale things. We should scale. Should means whatever it means, right? I'm not telling. Huh? But it's interesting to scale things in this way. Okay, and here is a very simple initialization in which you see that obviously the scaling achieves 0 error. Okay, very simple trick. To see that there exists at least one initialization so that gradient descent in this, for this function achieves 0 risk. Just take all the wi equal and all the I equal. So, or you can initialize it 0 if you want the w's. Then what will happen is that at initialization, and this is not trained. So now gradient descent the risk, in the empirical risk. Let's call this capital W. Is equivalent to gradient descent in so all the neurons stay together forever, and so they behave just like one single neuron. So we come back, so the risk, the population error of WT of W hat that you get from this converges to 0. Or the neurons, they initialize at the same point, they will move together. They see the same landscape exactly, and they will move together by symmetry forever. Right? And so this behaves exactly as training a single neuron, and this will converge to 0. Okay, so there exists for this scaling at least one initialization for which you trivially see.
So if it is 1 over square root of n, and the initialization is 1 over square root, all of them are 1 over square root.
Okay, yeah, so you're right. Here I'm cheating because I'm changing two things. I'm changing the scaling and I'm changing the initialization. Okay? Okay, so what happens if you use the same initialization of the W, let's say random? So that was my third question that I had to ask. So the question is, what happens to GD or SGD if I use scaling, so this is what we call the mean field scaling. We use mean field scaling, and let's say Wi at the initialization that is not pathological as in that case, but for instance normal 0 ID, or let's say normal 0 ID. Any other question? So this is my question, and it's Haim question. Any other question? Everybody's interested in this question. And of course, okay, some initialization for the AI, if you want. Now, since there is this factor 1 over n, it's natural to think of this as an average over A and W. So I think it's illuminating to rewrite this as f of x and, okay, let's forget about it. That is the integral over r times rd of some A sigma W transpose times x, rho dA dW, where rho is the distribution, the empirical distribution of the A and x. Okay, so now the question is, I initialize this AI and WI, IID, Okay, so at the initialization rho, so I initialize AI, WI, IID with some rho 0, and so let me call this rho hat. Oops. 0. And then rho hat 0, of course, converges by the law of large number to this rho 0 as the number of neurons go to infinity. And the question is, of course, if now I look at time t, I run gradient descent or gradient flow for time t, does rho t empirical converges as n goes to infinity to a limit? And if so, what is this limit? So the answer is yes, and as physicists we are, those of us who did some physics are ready to believe that this is the case, and here is the heuristic argument. First of all, for any finite n, so let's think that we are doing online SGD. So for simplicity, let me call each of these parameters theta it. So these are d plus 1 dimensional parameters. And what does online SGD means that each time I do gradient descent with respect to a single sample, and I never revisit the same sample for simplicity. One could do also revisit, but doesn't really matter. Okay? So the time here is the number of samples, right? So in that case, what happens is that theta it, as the step size goes to 0, I'll do the heuristic and then state something a little bit more precise. Theta it will asymptotically solve, do gradient descent in the population error. Okay, well, the population error is just what it is, right? The finite width population error is the expectation with respect to the data of y minus 1 over n, sum over I, AI, sigma, wi transpose times x. The fact that at each time I do a stochastic step means that this is true only in expectation. In reality, I go in a direction that is random, so it's this plus noise. But when you take the step size goes to 0, the noise averages out, and this becomes this. So I guess this is something that in the statistical physics intersect neural network community first was used by Sad and Sola for any constant number of neurons. But in mathematics is convergence of Markov chain to fluid limits. So there is a general theorem of fluid limits, of scaling limit of Markov chain that starts with Kurtz 71. Okay, so this is correct, as the step size goes to 0, and I'll say something a bit more quantitative in a second. Right now, I'm just doing the heuristic to try to guess what is the evolution of routine. Which kind? I mean, but Robbins-Monroe doesn't give you the fluid limit. Just gives you the Robbins-Monroe doesn't give you the limit. It gives you the limit as t goes to infinity. Here is n goes to infinity. So the claim is.
No, but you're talking here about finite.
So the step here is the limit, sorry, not it's finite time, but step size going to 0. Okay? So here what I'm claiming, so the claim is the following. If I run online gradient descent, so let's say this is SGD, K, okay, so this is I, this is online GD.
So what is I?
SGD. I mean that it's the ith neuron. Okay, so there is capital N, so I
I lies on time. Okay, good.
I is between 1 and n.
Okay, good. Okay. And
So this is ith neuron.
And T is the step. Okay, good, good, okay.
So here is that
Sure.
SGD K, and so what I claim is the following. Okay,
Is K now?
K is SGD step.
Okay, what was T here? Okay, good.
Okay, so there are two objects. There is this, so this is online SGD after K step, and then there is the solution of this ordinary differential equation, right? So let me call it, this is continuous time I. Okay?
Convergence of this to this.
Yeah, so the claim is
And
that under certain suitable assumption, blah blah blah, what you have is that limit, or better, 1 over n, sum over I, 1 to n, and then theta. Now I have to rescale time SGD at time t, a step t over eta. So eta is the step size. Minus theta it. 2 is with high probability bounded by something that is like eta, and then here there is perhaps the dimension. Okay, so this means that if I take the step size small, I can forget.
this is not the fluid limit, this is something else.
So this is the fluid. This is
Okay, so this is not, I'm just asking Kushner and
this is not Robbins-Monroe because this is fluid limits. It's not Robbins-Monroe.
Kushner.
Okay, perhaps there is before Kurz. The first one that I know is
Very good, okay, so
yeah,
same story.
yeah. So this is very simple ODE limits, right?
This is the same.
And then, excellent. Now we can write this risk as you can expand the square and write it as a constant plus 1 over n sum over I 1 to n v of theta I. This is the cross product here, and then there is plus 1 over, let's say that I put a 2 here, sum over ij 1 to n u theta I theta j. Okay, where what are these? V theta I is just minus the expectation of my target function times sigma of let's say AI sigma of Wi transpose times x, and u theta I theta j is just the expectation of AI sigma Wi transpose times x, aj sigma of Wj transpose times x. Okay? Okay. So what's happening here is, okay, if I want to look at it as a physicist, this is what? Theta I dot is, I'll write it like this, minus the gradient with respect to theta I of v theta I t, theta I at time t, plus the integral of u theta I t theta in rho hat t and t d theta. Well, this is just the empirical distribution of the particles. So you can think of these theta as particles that have, one a potential and then a pairwise interaction, and then at any given time they have a distribution. An empirical distribution that is this one. All right, so I didn't do anything, I just put the risk in here. And then I have a term that I singled out basically all the term that depends on theta I, because the other doesn't. So the total force on particle I is, you tend to align with f star, with the function f star, and this is basically a repulsion from the other neurons. Okay. So you can imagine that as n goes to infinity. Disaster. Okay. As n goes to infinity, so let me call what? Let me call psi of theta rho. I'll define this to be this potential seen by a single particle. So it's v theta plus integral of u theta, theta prime, rho d theta prime. So this is potential seen by a particle. By a neuron, okay? And okay, so you can imagine that, or you will not be surprised if you're a physicist if I say that this will converge as n goes to infinity to a limit density, a limit distribution, not necessarily a density. And what evolution can satisfy this? Well, this density must satisfy the continuity equation. What is the continuity equation? That is dt rho t. And now I should remember the sign. And the number of neurons, neurons move locally, and the number of neurons is conserved locally. So it must satisfy the continuity equation. And this is the current, right? So all that we have to figure out is what is the current. Well, the current means how many particles flow, the density of particles that flow times the speed, right? So current is equal to density times speed, or time velocity. Those of you that are not physicists will forgive me, but after a week in Les Houches, I started.
Now we start talking.
Yeah. So the current is density times the velocity. This is rho t of theta. This is rho t pure pressure. And the velocity is just, we saw it, is the gradient of, is minus the gradient of psi. Okay, so we found a PDE, an interesting PDE for rho, right? That describes the infinite width evolution of this system. Okay, and the PDE is, okay, I'll write it here, is dt rho t plus divergence, this is a divergence of rho t gradient of psi theta rho t equals 0. Okay, so this is okay, this has different name because, of course, pairwise interaction of particles was studied for a long time. So people sometimes call it the Mekhin-Vlasov equation. It's a bit different from, and it has been studied a lot in the last 10 years because it has some nice connection with optimal transport. So the first one who proved this kind of limits PD was a mathematician, Dobrushin.
Well, Russians are all people.
Yeah. By definition. and it has been studied recently in mathematics by the optimal transport community. Starting, people like Villani, Ambrosio, Figalli, and all the analysts, etc., because it has a very interesting structure. You can think of it as a flow in the space of probability measure when you endow this space with the Wasserstein metric. So it's really, you can think abstractly as a Wasserstein flow, gradient flow. And this allows you to prove a bunch of things, right? Okay, so what we added to this literature is that we had some quantitative theorem that I will not state in full generality, but under, okay, let me not write assumption, suitable, so under regularity assumption. On sigma, F star, V, and U that I will not write. So you need, for instance, V and U to be Lipschitz with bounded Lipschitz function. For this application, you need sigma to be bounded. You need F star to have some tails, etc. V is my potential. So remember, this is really the correlation between X and. So in my example that I described before, if you take sigma bounded and
sigma bounded, okay. The assumption, are there more assumptions than about sigma bounded?
Well, you need that this is bounded.
Yeah, but in terms of the neural network.
In the term of the neural network, this reduces. These are just conditionals on sigma, right? Because.
Okay, so I'm saying if I have condition on sigma and F star, I'm done.
Yeah.
There are no extra conditions.
No.
Okay, good.
No, there are some conditions that.
So it will not work for a loop.
Will it work for Relu? I think it will not work for Relu because of the unbounded thing, right?
It will not work for
It will not work for Relu, but it will work to, if you.
Not for linear.
Yeah, if you not for linear, but if you.
I bet the linear case will just do as well.
I mean, okay, so.
Reduced to a simple
I'll tell you, the problem is the following. I'll tell you what is the problem technically. I know that you don't like technicality, but
after a weekend.
Yeah. But exactly because you don't like, you understand that this is really a technicality that limits us here. And, the problem is that if this is unbounded, say that this is Relu, now these are part of the quadratic of the parameter, so this goes quadratically. So this goes like a theta square, right? And now you understand that you have an ODE with potentials that are like theta square is difficult to control, right? Typically when you have an ODE, typically when you have ODEs, you want to assume that coefficients are Lipschitz continuous and things like that. And this is only locally Lipschitz. Yeah, and then you have to go, okay, so I think that the result holds, but just the theorem doesn't. Okay?
Logic for the student.
Okay, so under this condition.
What are the conditions on F star roughly?
Again, f star needs to be bounded. And I think the condition of f star are only those that imply that v and u are.
I know, but I like to think about sigma and f star because v and u are the microns.
Okay. So you need things of this type, right? That v is, so let's forget about the a's. If you don't have the a's, if you don't fit the a's, things become even simpler. So you want, this is just the expectation of f star of x times sigma of w transpose times x, right? And now what you want is, so f star plays a role because what you want is that the gradient of this is bounded, right? So what is the gradient of this is E of f star x and then sigma prime of w transpose times x times x, right? And now, okay, so now you need this to be bounded. So for instance, if you take our example, that is, this is, let's say, phi of u star transpose times x, sigma prime of w transpose times x, now you can, and x is Gaussian, now you can compute this by integration by parts, right? So this will be some.
Bounded in W, right? That's what you mean.
Now what I mean by bounded is independent of the dimension. You need all of these things. Is
No, but it bounded in terms of how it depends on W, no?
yeah, also how it depends on W.
For fixed dimension, I mean, it's not dimension. What dimension of x, d?
Yeah, so the crucial thing is the dependence on D. I mean, okay, let me finish the statement, right? Okay. So you take some distance between this empirical distribution that I wrote there and the solution of and you take this that less than n. Okay, let's make it simpler. You evaluate the risk on a finite number of neurons and you evaluate it at theta I t, theta I k SGD. So you take finite number of neurons, look at the test error, you learn k steps of SGD, online SGD with k equal t over eta, okay? And you compare this with the risk with infinite number of neurons on the solution of this PD. So in one sense, and then this is the test error for my infinite width limit, and this is finite width limit. The claim is that this is bounded by constant, and then there is a factor like square root of the dimension, and then there is a factor like the step size, and then a factor times 1 over square root of n, and then a factor e to the c, t to some power. And t is the maximum. Oh, sorry. So I look at any time of order 1. Okay, so I look at any time.
It's exponential, it's plus.
Yeah, so this is positive. So this means that, so this error for any constant t, this error goes to 0 when I let the step size to 0 and when I let the width of the network go to infinity. So this means if you take, if the time is finite,
The exponent is positive and the
positive.
So eta is to scale, like exponential is small.
No. So t,
No,
okay.
but in order for this to be something reasonable, capital T is loud.
So capital T, I'll take capital T of order 1. Capital T is the continuous time. So it's independent of the step size.
With the continuous stuff. So I'm saying if I run it long, the longer I run it, then the eta, in order for this to be small, eta is to be e to the minus t small.
Okay,
Which is the unusual. Usually it's a, I don't know, n depends on d or n.
Okay, so let me say when this theorem is useful. You run the PD, so it's useful when can take t a constant, and when t is a constant, R infinity of rho t is small, is less than epsilon. Okay? So if there exists a capital T that is a constant, such that you run for that time and the test error becomes small, then I'm in business. This business is a constant, and in that case means that I need only to take n much bigger than some polynomial in D and eta much smaller than 1 over T.
Smaller than e to the minus, I don't understand. It's constant, but still it's smaller than e to the t cube. Whatever. I mean, that's the, you have this effect. What can you do?
But this thing T will be fixed, right?
I know it's fixed. I know you don't want to think about fixed, but C doesn't depend on this T, right?
This C doesn't depend on this T.
So, okay, so eta has to be smaller than 1 over C and then 1 over, e to the minus ct cube.
Right. Yeah, I agree. Yeah, I agree.
But so if T is large,
Yeah. So the approximation.
it's fixed, but it's 100. Okay?
Yeah.
We're stuck. E
Okay.
to the minus, 100
Okay.
cube.
Okay, this is a bound, right? So I mean, if I was a physicist, I would say,
If you're a physicist, you will not accept this.
I'm a physicist, right? Life is good if you're a physicist. Why do I bother?
Anyway, it's not.
Okay.
So, but
Okay. So
you something else because I have to ask more.
now we have to come back to the original problem, right? Okay. So I have to come back to the original problem. So. And now I'll be once more, I hope not to be a physicist so far. But okay, the question is, can we solve this PD? So can we solve this? Okay, the truth that in general solving this PD is very difficult, right? If you give me a general V and U, then I have to integrate it. If the dimension is large, I have to discretize the dimension. This can be extremely hard, but this can be done numerically. Now I'll pretend that I'm Giulio. I'm another physicist. Can be done numerically, and you are invited to work on better numerical solver, as Giulio would say. But I will not work on them. It can be solved efficiently if the model has a lot of symmetries, okay? So if the model, so yes, numerically, and perhaps something analytically, if the model has symmetry. Symmetries. For instance, let's go back to our example, right, that we started with. F star of x is phi of u star x, and then x is isotropic, right? So let's say uniform on the sphere or whatever you want, Gaussian or. Then it's clear that all of this potential only depends on theta. What matters are three things, right? So theta in general is a neuron. It's an object that is d+1 dimensional. So this is the dimension in which the PD lives. But if there is this symmetry, the solution. Okay, the solution, rho t, will be invariant and if the initialization is isotropic, will be invariant under rotation around U star. Around U star. Okay? At the initialization, I initialize with something that is invariant under rotation. My distribution is invariant under rotation, etc. So that will be invariant under rotation under U star. Notice that this is a symmetry that only, arises in the large width limit, right? Because at any finite width, you have finitely many particles and will break this symmetry. Okay? So in particular, now what will matter is not this d plus one dimensional parameter, but will be AI, will be the projection of Wi in direction U star, and then will be the norm of the orthogonal component of Wi. You can decompose Wi in the projection. Okay, I should write it not.
Do you require F star to be deterministic?
X star.
F star.
F star to be deterministic. Yeah, you can add noise. Yeah, in the limit the noise disappears, right? Because in general, so perhaps you can, in general, what you have is V of theta will be E. It will be minus E of yi, and then AI, A sigma W transpose X. Right? So this is where theta is always AW, right? Now, if Y is F star plus noise, the noise. Right. I mean, here we'll add the constant to the risk, right? Basically, what happens is since I'm taking many steps, each time I visit a new sample, the noise averages out. Okay, so now, what I wanted to write what I wrote in a corner in a place that can be seen actually by people. So what matters? So instead we have a dimensionality reduction in which what matters is not theta I t, but not W, not the pair AI Wi t, but what matters really is, of course, AI t, and then the projection around U star of Wi t, and then the projection, the norm of the projection orthogonal. Okay, and now, so instead of having a PD in D plus one dimension, you will have a PD in 3 dimensions. Okay, now this can be solved numerically, right? Now analyzing this PD in 3 dimensions is still non-trivial in, so the point, so what is the initialization for the PDE initialization? What matters is this one, so this will be rho t of A, let's call it this S and R, S and R, I. The initialization will be in S, will be something like this, will be Gaussian, basically Gaussian, with variance 1 over square root of D. If I look at the distribution of the projection along U star of the initialization, if I take initialization random and isotropic, will be very peaked. And in the orthogonal direction will be basically 1. So this R will be centered around 1.
So now we assume we assume n goes to infinity, but now we assume d is 1.
Right. So we took first n to infinity. I'm just saying qualitatively what is. Now this you can solve numerically for any constant d, right? D only appears as a parameter, so, and the role that it plays d, this PD, if you write down d, will not appear really, but the place where it will appear in the initialization. Now, okay, so you know, okay, one can show, it's easy to show, it's easy to prove. Let me tell you what is easy to prove. Easy to prove that if I look at this risk achieved by the PD, so there exists for any epsilon, there exists T of epsilon such that the risk achieved by this PD at time T is less than epsilon. And this T doesn't, T of epsilon and dimension. Sorry. Sorry? Sorry, epsilon. Okay, so this, if I fix the dimension, is easy to and it's easy to check that this is also true. So really, okay, let me call this variance alpha square. Really, the time that it takes to converge depends only, if this alpha is bounded away from 0, then converge in time of order 1. So if initialize with some correlation with the data, any small correlation with the data, then we'll converge in order 1. Okay, there is no theorem, unfortunately, at the moment. So open, mathematically open, prove that actually this T, epsilon, and alpha square actually doesn't depend on alpha square. Now, as this becomes thinner and thinner, the initialization is singular, and PD analysis method that allows you to prove this cannot be applied to singular initialization. Right? So this is what you see empirically if you solve this numerically. In three dimension. Okay, so what is the summary of this thing? And I stop here because this is, first of all, it's lunchtime, and then it's the end of what I know. That if I look at n,
It's not a reason to stop.
no, we always go towards what we don't know, but it takes food to go there. Well, the summary of what we know is that if you do, the neural tangent scaling, I don't know what is the shape of this curve. So if you neural tangent scaling, the risk as a function of the width goes to a bad value. But if you do the mean field scaling, okay, other color. And here, of course, I don't know. But at large n is good. Of course, I would imagine that this stays down, but okay, I don't know. As I don't know whether this is monotone, this could go down and up. I don't know that. But okay, so this is what I know.
On the blue line, you wouldn't know what to put. Spreading n over b n square over b.
Yeah.
Doesn't make much sense, would it?
Yeah. So okay. So what this theorem that I said here is really that n much bigger than d is what matters. And now the sample size somehow I've hidden under the carpet, but in this analysis, the sample size, since I use one sample per time step, is equal to the number of time step. So it's T over eta. And now if you look at the bound, I need to take, if capital T is of order 1, I need to take eta of order 1 over d. So you take that this is of order t, constant times d, which is nice because it's the optimal sample size, right? If I want to learn a ridge function, I need at least 10 samples.
So I had a related question. Any way to get the constant from these equations? I mean, to go to the non-online case in this case.
To get the, what do you mean the constant?
To get the constant, like to know
how many sample? Well, the constant here depends on depends on two things: how small you need to take, how big you need to take t, right? And how big you need to take t is basically the solution of this partial differential equation. Okay, so if you solve this part, this t will depend on epsilon, right? That is the risk that I want to achieve, right? So you run the partial differential equation and you see when you achieve risk 0.01.
Sure, but could we also write it in the batch case?
Okay, so that's a good question. Actually, the PD you can write it in the batch case, except that then what happens is that what matters is not, for instance, v theta, that is again minus e of y. Let me write sigma of x and theta. But what matters will be the empirical v. 1 over sample size of sum over I 1 to n yi sigma of x times theta, xi datum theta. Right? So what will matter for finite sample size, I mean, if you don't do online, you will do gradient descent in the empirical error, not in the population error, so all of this average. And the problem is that this is nastier than that guy. But, okay, something that I was saying, I don't know to whom, to Haim yesterday at lunch, is that if you ever, in the optimistic case, and perhaps this goes in the big question chapters, in the optimistic, where will the theory of this stuff evolve? I don't think that will evolve in the same direction as the current theory of high-dimensional statistics or machine learning, or the previous theory is. That is, I have a model for the data, I have an algorithm, and I prove that the algorithm works for that model of the data. That would be like pretending that a physicist takes a dishwasher and proves to you that the dishwasher washes the dishes. That's ridiculous, right? These systems are too complex. What we can hope to have is multiple kind of macroscopic models of these systems, and then connect them to each other, and as well. And from this point of view, it's okay that one has different theories of the same phenomenon, because the different theories will capture different regimes and different aspects, and it's not a matter of. So we have all to learn from physics.